what's the deal with ideal versus a real gas? We've been learning that gases are unique from liquids and solids because they have no intermolecular forces. That's what we actually call an ideal gas, because most of the time gases are moving so fast and they're in such a big area, they're not really close to each other. There's no forces that cause these particles to stick together. But if we cool down a gas and then we decrease the volume, the closer they get and the lower the temperature, they actually can stick to each other, those gas particles. Just a little bit. It's not a very big difference, but just a small difference. All of the calculations that we will be doing in this class are for ideal gases where we assume there are no intermolecular interactions. So that's something to understand, that gases do actually stick, but only under special circumstances, so we can ignore it for most of the problems that we deal with in this class. If we see any percent air, hint, hint, your analysis for your lab today, you want to think about this as a variable that could be influencing how your gas is behaving. These are two concepts that you should have already picked up from the homework assignment lab, even more gas laws and properties. Diffusion, of course, the movement of particles from a higher concentration to a lower concentration. Basically, your gas particles will mix. That's why if someone farts in the room, the smell will not be bad forever. The particles will diffuse to the point where it's not. You guys should laugh. What's wrong with you? I mean, we're still in high school, but like farts are still funny. I mean, come on. All right, moving on. Effusion is different. Effusion is what happens before the fart enters the room. It's through a small hole. And that's you should really be laughing right now. I'm a little upset that like none of you guys are finding this disgusting. All right. Effusion is the passage of a gas. Come on. Come on. The passage of a gas under pressure through a tiny opening. Come on. Like, no one? These are horrible.
Just keep talking.
Fart jokes aren't funny for you. All right, whatever. Anyhow, effusion, the passage of a gas under a tiny opening. There are factors that influence how fast gas particles move about. So actually, we would want the temperatures in a room to be really high if someone farted because we want the gas particles to mix as fast as possible. There's a downside to it being really hot when that happens, though, because the particles are moving faster, we smell more of it as opposed to less of it. But if it's like cold, then the smell just stays in one part of the room for a while. If it's hot, it diffuses really quickly, all right?
Smells a fart forever.
Yeah. Exactly. So, velocity, how fast the particles are moving. Obviously, the higher the temperature, the faster they diffuse. And the mass of the molecules. The lighter the molecule, the faster it moves. So, if you're looking at the average speed of molecules, particularly with diffusion, hydrogen moves the fastest. Carbon dioxide, and the one that would make it really nasty smelling, a lot of the sulfur dioxide that comes out in that, part, is usually on this end. So it actually moves a lot slower than hydrogen gas. Dalton's Law. Dalton's Law is something that I actually want you to write down as notes on your piece of paper. Dalton's Law is one of the formulas we're going to have to use for our lab today. If you have a bunch of different gases mixed together, the pressure of all the individual gases added up equals the total of the overall pressure of that gas. So if I mix hydrogen and helium and nitrogen, I would have to add those up together to find out the total pressure of that gas. It's one of the easiest formulas we ever deal with. Just think that like when you've got a container of gas and you want to know what the overall pressure is, you have to add the pressure of all the components of that gas. You guys have any questions about that particular concept? What I really want written down is not necessarily the definition, but I want that written down. A, B, C are just variables to represent all the different components of the gas, okay? That's mixtures. And all gases are usually mixtures. It's really tough to generate a gas that's just pure. And you're going to see why when we get to our lab today.
Hold on, pause.
I will pause. For a future posterity podcast, that is Alicia Laws that wants us to pause. Since I'm probably going to use this for the rest of my career.
Thank you. I appreciate my little 15 minutes of fame.
That's right. Every other Mr. Barron class is going to get you out of it. All right, now I got to move on. All right, so oxygen can actually be toxic to us. If you are at deep depths under the water, the partial pressure of oxygen gets to the point where it actually becomes toxic. That's why the mixture of air, whenever you do deep scuba diving, actually has less oxygen in your gas container than at normal sea level. So partial pressures do increase, and it becomes dangerous. There is a death zone for oxygen. It's kind of crazy. All right, this is the point of our lab today. Today we are going to be doing, believe it or not, the same measurement we did, in the beginning of the year. Remember the dry ice lab where we took the dry ice, we put it in a bag and inflated the bag, we replaced the gas with water, and then we measured the volume so we could get a relationship between moles of carbon dioxide and volume of carbon dioxide. We're actually going to do the same thing today, but we're going to be using a much more technical technique, a much more specific technique, a much more precise way of doing it because we're going to be using gas collection tubes, which are called uniometers. This lab we're going to be doing today is the same as one of the labs in the AP curriculum. There is overlap between the first year of chemistry and AP chemistry, and this is one of those labs that overlaps. Now, if you look at it, we need to know that molar volume is 22.4 liters per mole at STP. That is something we need to write down. 1 mole equals 22.4 liters. 1 mole equals 22.4 liters. But that's only true, 22.4. That's only true at standard temperature and pressure, STP. Standard temperature and pressure is the next thing we need to write down, and it's that standard temperature and pressure is 0 degrees Celsius and 1 atmosphere. So at 1 atmosphere, 1 mole will be 22.4 liters. I'm going to write that down actually on my visualizer so that you guys can see more precisely what it is. And we can label this as our actual that we're going to compare our measured value to in our lab. And that's that 22 point, oops, wow, I already messed that up. Actual, and it's 22.4 liters equals 1 mole. And that's that's my crazy at sign, at STP, which is called standard temperature and pressure, and that's 0 degrees Celsius and 1 atmosphere. That's information we need to know for the lab that we're going to be collecting data on today. Now, there is something else that we need to be aware of to be successful in this lab. The other thing that we need to be aware of is something called Gay-Lussac's law of combining volumes. It's a stoichiometric ratio thing. Remember we used in stoichiometry mole-to-mole ratios, and you took the moles of, say, hydrogen, and then you use the coefficients to create a mole ratio to change how much of a reactant you had to predict how much of a product you'll produce. Well, the cool thing with gases is that moles and volume are equivalent to one another. You can use the volume or you can use the pressure of a gas, and then you can basically do the same stoichiometry calculations. I'm going to demonstrate that for our lab today right now. If I have in our lab today, and this is something I want you to write down, you are going to be, say in your lab, we have magnesium, solid magnesium, and in our lab we're going to react it with aqueous hydrogen or aqueous hydrochloric acid. What's going to happen is we're going to generate hydrogen gas and magnesium chloride, which is going to be aqueous in the solution we're working with. It's a salt. I have to balance my equation, so I'm going to put a 2 in front of there. Now, just to remind yourself about the ratios we deal with in chemical reactions, say I start off with 5 grams of magnesium. If I want to figure out how much hydrogen gas I'm going to produce, I'm going to change it into moles first by canceling out the grams. This is the molar mass. The molar mass of magnesium is 24.31. Then we can go straight to the mole-to-mole ratio. I'm starting here. I want to figure out how much hydrogen gas I'm going to generate. So we go to H2, we cancel out magnesium, and that of course is our mole-to-mole ratio. The numbers come from the coefficients in the chemical equation, so it's a 1-to-1 ratio. And that will tell us the amount of moles of hydrogen I have. Remember, the magnesium cancels out, the grams cancel out, the moles cancel out such that I'm only left with moles of hydrogen. Now, imagine we did this experiment at STP. If we did this experiment at standard temperature and pressure and this classroom was 0 degrees Celsius and all water was frozen, then we could use this ratio. We could go 2 liters and cancel out the moles, And as we see from our molar volume up top, for 1 mole of a gas, it takes up 22.4 liters of space. The moles would cancel out, and that would tell me my answer in liters of hydrogen. I don't know the exact number because I haven't gotten it out on my calculator, but I'm assuming most of you guys could set it up. Do you guys have any questions about that setup? All right. Now, I'm going to pause